Welcome back. All right. Like I said last time, I hope you've done your practice. Okay. Looked at some worked examples, done your practice. What we're going to address is this massive error, okay, that is occurring in our ranges, which is giving us this massive range. Okay. It's so many numbers and it could be anything in between. It helps, but not really. Okay. It shortened the range from negative infinity to 14 and 30. Okay. It shortened the range, but it's still not very useful. Okay. We don't know whether it's 15 or 29, whatever. Okay. So what we do instead, all right, we then realize something. Okay. We realize that when we first did this problem, okay, when we first did this problem over here, we use one big rectangle, one small rectangle, one upper, one lower rectangle. Okay. So we did that and we got a massive error range. Okay. Extra space, a lot of it. And then what we did instead was we used more rectangles. Okay. And as you can see, the error range is still there, but when you compare it to that's it. When you compare it to this, right, it is a lot better. Okay, a lot better. So what we can do to further improve is to simply use more rectangles. Okay, so if we have your function like this, all right, and this is your 4, this is 0. Okay, you can use, instead of 4, you use 6 rectangles. Okay, I believe that's 6. Or instead of 6, you use 8 rectangles, 10 rectangles. You use more and more rectangles to get less and less error. Okay, you get closer and closer to the actual value. So let's just note down what will happen as you increase the number of rectangles. Okay, so first of all, what is going to happen is the width of each rectangle is going to decrease. Okay, obviously, because you're trying to cram in more and more rectangles in a finite space, you have to make them smaller. Okay, that's pretty obvious. The second thing is a bit more annoying, is that the process of finding our area, okay, it gets a lot longer. So instead of this, you would have something like f of 0, blah, 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 f of 4, 5, and depending on how many rectangles it gets a lot more. So you have to compute a lot more, and it's a bit tiring. Okay, so process gets longer. Okay, so in order to avoid writing so much, we are going to change up our notation a little bit. Okay, so we're going to look at this. All right, we're going to erase this because we do not want to write that much. Okay, when we erase that, now we're going to say, well, this area lower, okay, lower area, what is it in the simplest form? What is it? It is the width of each function, width of each rectangle, sorry, the width of each rectangle, I'll denote it by a small w, times the height of each rectangle, okay, times the sums of heights of each rectangle. Okay, now what are the heights? The lowest points in their regions. Okay, so they are the sums in here, in this bracket. It is the sums of the lowest points in each region, in each portion. Okay, so whenever we are dealing with a lot of sums, we use this notation called summation. Okay, sigma is the Greek letter for this. Just had to put it out there. Summation and sum. Okay, all right, it is just representing a lot of sums. Okay, and now what I'm going to do is I'm going to say this sum starts at I equals 1 and ends when I is equal to n. Now what is I? I'm just going to point it out right now. Don't worry. So this is L of I. Okay. So what I've done here is I'm literally just saying this is a function that I have just come up with, which is the lowest point, okay, because that is what the heights are, lowest points of f of x in ith portion. Okay, because that's what we did, right? That when we were doing this whole process, we went, okay, in the first region, all right, this is the lowest point, okay? Hence this, all right? In the second region, this. Third region, that. That's what we did, okay? And that is what I'm literally saying, is that you get all the lowest points in each of the regions. And you start with the first region and end with the nth region, okay? So start with the first and end with the last one, and you sum all of them, okay? You sum all of them, and you would get your area, okay? That's what we've done, and we've just written it in a much simpler way. And this W doesn't need to stay a W because we need to make it a bit more precise. What I'm going to say is this is the width of each rectangle, right? So it is the total width, okay? So the width of the total range. In this case, it was 4 width of the range divided by n, which we know is the number of rectangles, or the number of portions. Okay, so now to finalize it, this is our notation that we will be using throughout from this point onwards, okay? So now that we've changed up our notation, let's get back to our epiphany that the more rectangles, the more stuff, okay, the more precision, okay? So as n approaches infinity, maximize it, okay? Just use as many as you can. Precision, okay? So our precision approaches perfection, okay? So if we start using as many as possible, our precision starts to get perfect, okay? What we are really saying is that as we use many rectangles, all right, we start to have no error, okay? All right, and whenever we do this, okay, we're taking steps towards infinity, we are approaching infinity, what would we do? We would use limits, okay? So we are saying that this, okay, this, and now what I'm saying is this is the perfect AL, so the perfect lower area with no error. This perfect is the limit as n approaches infinity of this thing here, okay? So as n approaches infinity, because this is just an area, okay, this is the area. As n approaches infinity of this, all right, we would get the perfect lower area. Same thing would happen with the upper area, okay? As limit of n as it approaches infinity, okay? Same thing, except this time it would be h of I. Highest point instead of lowest point, okay? Straightforward. So we are saying that as we include more and more rectangles, right, there's no error. It doesn't go above or below the curve. It is exactly at the curve, okay? So what would happen then is that because this is perfect and this is perfect, okay, both of them have no error. They're both on the curve, all right? Like don't go above, don't go below. They both get the same value, okay? As n approaches infinity, when n approaches infinity, okay? They both get to the same value. Like if you visualize it, right? So these are the rectangles that are below, these are the rectangles that are above. They get closer and closer to the curve, and they match the curve exactly. The lower one matches it, upper one matches it. So because they're matching the curve, they're matching at the same point. They have the same heights. So the areas are the same. Okay? Also, when this happens, all right, you get your definite area. This is your true area, the area under the curve that you are looking for. Now we know that in order to get the exact area, we just have to use infinite rectangle. Lie, okay? Nothing that hard. So we just put someone at work for the rest of his life. Infinite is just keep doing it, okay? All right. So that is the process. Obviously, we can't do infinite rectangles. We can do a lot to get as close as possible. We get a very, very good approximation, okay? And that is mainly the process. Now, before we sign off, all right, I want to note that mathematicians, annoyingly, did not find this A fancy enough as your area. So what they did was they introduced this notation, Okay, let me just rewrite that in a better way. Okay, they introduced this notation. So the area is equal to this. I've written it. I'm going to explain it. Calm down. Okay, so this means sum. Okay, it's just a stretched out S. Stretched out S. Okay, and the S stands for sums. Okay, so it's just a lot of sums. Okay, that's what we were doing. We just added a lot of rectangles. So the sum makes sense. A is the start of range and B is the end of range. Okay, again, nothing complicated. F of x is the function you're looking at, and d of x is what you're looking at, what the variable is being used. Okay, so that is your notation, and this notation is called the definite integral. Okay, the definite integral. Okay, now that is what we were trying to get to. This notation, this thing, this shows the exact area underneath a curve, underneath f of x from A to B. Okay? That is what your definite integral gives you. Okay? Now, for now, this definite integral has nothing to do with the antiderivatives, the integrals we learned before. Okay? It has absolutely nothing to do with it for now. Okay? Trust me. Later, you will learn the importance of it and how they're connected. And I want to hype up this next lesson as much as I can, because when the people realized this connectivity between the area under the curve and antiderivatives, they went crazy. Okay? There was like a whole epiphany. People were like, oh, woo. So I want to hype it up as much as I can as well. So yeah. That is it. That is all for this lecture. So yeah, go do more practice questions. Okay, start finding exact areas, or try to, and yeah, we'll meet later for this epiphany. Yeah.